Let's put it in this way. I'm a physicist and I work on NMR relaxometry for a long time. And I know that this is not easy method and that there's a lot of things which one might have problem to understand. And this is especially very, very difficult if, how to say, being frank, your background is different. I mean, not physics, because the problem is that NMR relaxometry is just a kind of advanced phenomenon based on quantum physics. And if you do not start from the beginning, it's really like, it's hard to understand what the story is about. But you see, before I start, I can tell you that actually I have similar feeling when it comes to food science. And this is more or less like with Martin, we write papers. I mean, I write my part, he writes his part, and we try to understand and put it together. Okay, so I will start just from very, very simple things. We will see how much time it will take. I assume that I'm supposed to give a kind of tutorial. So let us start with basic things. To perform NMR relaxation experiments, we need some specific nuclei. And actually, in most cases, there are hydrogen nuclei. Well, of course, as you know probably already, one can perform nuclear magnetic resonance experiments for different kinds of nuclei. However, I suppose this is not what really will be doing much, at least not to a large extent, taking into account that our project is about food. So I suppose that majority of our studies will be just 1H NMR studies. And then what is the trick? Actually, something very trivial. Yeah, well, the hydrogen atom consists of a proton and electron. Yeah, so the nucleus is just a single proton, and the proton has a magnetic moment. And now is the trick. If you take a glass of water, what we'll be doing in a second, or I don't know, being more abstract, if you take a large collection of hydrogen atoms, and there's no magnetic field, the magnetic moments of the nuclei are oriented completely stochastically, just with the same probability in all possible directions. But then you apply external magnetic field. This is what we are doing when we are performing NMR experiments. And what is happening now? This is just when the quantum physics starts. Because actually it turns out that there are only two possible orientations of the magnetic moments of protons with respect to the external magnetic field. They can be oriented parallel or anti-parallel to the magnetic field. It's not that there is just, for instance, magnetic field and the orientation is like that. I don't know, 47 degrees or something like that. Only parallel or anti-parallel. This is what quantum physics says. Yep. This is a kind of first surprise because usually when you study some principles of NMR, especially NMR relaxometry, there's a lot of so-called classical approaches. You are told about precession, this type of stuff, and so on. People go rather in the direction of mechanics, not quantum physics. But I have to say that the concept based on classical physics, okay, it's a kind of natural consequence. However, to me, it is much more difficult to understand. I think that really everybody is able to understand the, how to say, proper, not simplified quantum mechanical picture. But the first thing is just that there are only two possible orientations. You see, remember, for instance, there are well-known jokes about Schrödinger and his cats, yeah? So there is a Schrödinger sitting in a waiting room at a veterinary doctor, and Schrödinger keeps a box, and the box is not transparent, there's a cat inside. And the veterinary doctor say, oh, okay, you see, Mr. Schrödinger, there are two possibilities. Your cat is either alive or dead, yeah? And people are laughing at that, and in fact, nobody knows why. I mean, really, when this is like, we treat this like, because we are laughing because we think it's just trivial to this extent, so one can laugh. It's like saying to somebody, oh, you are healthy or not healthy, you know, and this is the invoice, yeah. So people can be laughing at that. So somehow this is also why majority of people is laughing at that, but there is something much deep into that. Namely, it's just the fact that systems, generally understood, atoms, electrons, molecules, can be only in some well-defined states, not like they are. So this is the first thing. Magnetic moments can be oriented parallel or anti-parallel to the external magnetic field. But then there's energy associated with this orientation. And actually it happens that for one of the orientations, the energy of the interactions of the magnetic moment of proton with the external magnetic field is lower. Well, because it's not equal, yeah? So for one of them is lower. It's again a kind of trivial statement. But now is the point. Now is the point when something what is called Boltzmann distribution becomes important. Because there's a principal law of the nature that each molecular atomic system wants to be in a minimum of its energy. Everything goes to take minimum of energy. It's like you see, you are entering a room and there's a certain number of seats and the number of seats is smaller than the number of people and everybody wants to sit, yeah? And the desire, how to say, to occupy the state of a lower energy is stronger when the difference between the energies is larger. So it's like if you can only stay or sit, you will be really fighting for the seat, yeah? But if everybody can sit, but some of you more comfortable, some of you less comfortable, then the fight will be not so, not so strong, yeah? You can easily accept not to be in the more preferable position. So the same is happening here. So Boltzmann distribution gives a probability that the state of a given energy is occupied at a given temperature. And, well, the state of the lower energy is occupied more. So consequently, you have a number of magnetic moments oriented parallel and the different numbers of magnetic moments oriented anti-parallel. Some of the magnetic moments compensate, but because there is a difference in the population and there's a lot of magnetic moments, because we have a lot of hydrogen atoms, so consequently, as a result of these non-equal populations, the sample gains magnetization. However, it is like that. Let's imagine that we do not have any magnetic field at the beginning, then we apply a magnetic field. Now, okay, so at the beginning, the distribution of the orientations of the magnetic moments was completely chaotic. Now, only two orientations are allowed. Now, okay, so the magnetic moments must somehow change their orientation. But this process takes time. And to give you some ideas, for instance, for water in bulk, it takes about 2 seconds at room temperature. This is a very long time, actually. Usually it's like milliseconds, let's say. Tenths of milliseconds. However, it needs time, this process. And in addition, it needs energy. And, well, there's a general term which describes relaxation. By relaxation, one understands that it is reaching equilibrium. So then you might be a little bit surprised if I tell you that actually the time which is needed for the magnetic moments to assume the positions according to the Boltzmann distribution, so some of them parallel, some of them anti-parallel, and the proportion between the two orientations determined by the Boltzmann distribution, the time which is needed for reaching this state is called spin lattice relaxation time. However, reaching just this state is nothing else like reaching equilibrium at a given magnetic field and at a given temperature. So the process of the reorientation of the magnetic moments is just nothing else like relaxation. And the time needed for the orientation is just our relaxation time. But you see, now is the trick. Because imagine that you have some magnetic field. I will show you some pictures later. You have a magnetic field. You reach this so-called equilibrium, and then you change the magnetic field. You reduce it or you increase it, because this is what we do in our experiments. And there are still only two energy levels allowed. However, now the gap between the two states, the energy gap, will be higher or lower because it's proportional to the magnetic field. So how to say, according to the Boltzmann distribution, at higher magnetic fields, the difference between populations of the two levels is much larger than at lower magnetic fields. So if you change magnetic field, the two energy levels must repopulate. Yeah? The difference between the populations must increase in case you increase the magnetic field compared to the previous value, or decrease in case you reduce the magnetic field. But this process requires exchanging energy with the surrounding, because just the energy levels are different. Yeah? So if more protons is supposed to go up to the higher energy level, this requires energy to be taken from the surrounding. If more protons is going to reach the lower energy level, they will, how to say, as in the case of this transition, some energy will be released, and there must be something what will be willing to take the energy, just to eat it, how to say. So the energy is taken from or given to other molecules and atoms in the vicinity of the atom. The nucleus of each is relaxing. Yeah. So, and all the molecules and atoms and around are called lattice. So therefore, this is spin lattice relaxation because it includes exchanging of energy with lattice. But well, quite often you will be told that actually, which energy is exchanged? And this is the point. Because if I would say, I just wrote here that the energy needed for the orientation is taken from molecular motion, translation, diffusion, or rotation dynamics, for instance. However, this cannot be treated so literally. What is the point? Because one could then easily imagine that there is a molecule performing motion, the molecule has a kinetic energy, and the energy is somehow taken. It's not so simple. First, it must be a kind of link between the relaxing nucleus and, let's say, other species in its surrounding. And here is the trick. The magnetic moment of the proton or any other nucleus interacts not only with the external magnetic field, but also with magnetic moments of other nuclei. So for instance, if you take a glass of water and you think in terms of a collection of water molecules, if you look at a single hydrogen atom and its nucleus, the magnetic moment interacts not only with the external magnetic field, but also with the magnetic moment of the second hydrogen atoms in the molecule, and also with nuclei of hydrogen atoms belonging to different molecules, yeah, but being somewhere in the vicinity of the relaxing nucleus. And the physical nature of those interactions is that they are magnetic dipole-dipole interactions, because two magnetic dipoles interact. Magnetic moment of one proton with a magnetic moment of another proton. Yep, so this is how they see each other. However, what now? Because of motion, just ordinary Brownian motion, like translation diffusion or rotation diffusion or any kind of vibration dynamics, the magnetic dipole-dipole interactions fluctuate in time. Because, well, look, for instance, not going into details, each interaction depends on distance, yeah? So for instance, if I take two water molecules, magnetic dipole-dipole interactions between protons belonging to different water molecules change in time because distance between them changed. Because as a result of diffusion process, the molecules sometimes become closer, sometimes more distant, and so on. So the magnetic dipole-dipole interactions fluctuate in time. And now, depending on the strength of the interaction, I mean its amplitude, depending on the time scale of the fluctuation, I mean the time scale of the motion, and third thing, depending on the type of the motion, I mean its mechanism, then the efficiency of exchanging the energy between the relaxing nucleus and the lattice is higher or lower. And higher efficiency of exchanging energy means faster relaxation process. So in this way, the relaxation times or rates are sensitive to the dynamics in the system. So this is merely the path, how it works. And here you might have a kind of nice picture. Namely, yeah, you see that there's the stochastic distribution of the magnetic moments. Then only two orientations are allowed. And this process of reorientation, yeah, here, means that progressively, the magnetization is built. Okay, now you can be scared a little bit, but you see, this is the trouble, because I would really like that we go through this math, and I believe that we cannot go through this math. This is the only math which I prepared, and I know that it sounds horrible, looks horrible, but it's not the case. Look, first, you do not learn them by heart. This is the point. Everything is written. And there is software for calculating those things. So you do not need to implement anything. It's just only understanding what it is about. So we have, let's say, two water molecules. As I said, just the magnetic moments of protons interact with each other. They can be of intermolecular origin, but they can be also of intramolecular origin. When I come back a little bit, and if the time constant of this process is called relaxation time, its reciprocal value is called relaxation rate. And now, there is relaxation theory. And you see, I do not want you to become specialists in relaxation theory. However, I somehow believe that if one understands just this slide, one can do everything. And this is possible. Look at that from this perspective. The relaxation rate stems from two kinds of interactions within the molecules, which we can call intramolecular, and between the molecules, which we can call intermolecular. So the relaxation rate measured in experiment, I will show you some examples shortly, have two contributions from intramolecular and from intermolecular interactions. This is the first point. And this is not so difficult to get. Then there are expressions for the intramolecular and intermolecular interaction, relaxation rates, and they look horrible. But it's not really like that. Let us look at the intramolecular. 2/5 is just 2/5. You do not need explaining. Now, you have something which is called IH, and this is spin quantum number of proton. And spin quantum number of proton is 1/2. So come on, 2/5 times 1/2 times 3/2. Yeah? This is very easy to get. Then you have here something, which is called dipolar relaxation constant. I can give you a well-defined expression for that, but actually it is not so interesting because it includes things like geomagnetic factors of protons, some well-known physical constants. And what this thing includes is just power 6 of a distance between the two atoms in the denominator. Sometimes just one, and this is quite convenient, one just denotes this thing, everything what stays here, as just dipolar relaxation constant. But what you should know here, that this strongly depends on the distance between the interacting nuclei. Then you have something which are called spectral density functions. And they are taken at the so-called resonance frequency and twice the resonance frequency. Here I should say that actually resonance frequency is proportional to the external magnetic field, and the resonance frequency is nothing else as the energy difference between the two allowed energy levels. And it is proportional to the external magnetic field, just geomagnetic factor of protons times the external magnetic field. Now, okay. I'm not going to talk about what spectral density is. Maybe if I will have some time, we'll see how it will develop. And that we are making some Fourier transforms and so on. I would not say like that. I would make it very simple. Namely, the shape of those functions, the form of those functions, depends on the kind of motion which is responsive for the fluctuations of the magnetic dipole-dipole interactions. In case of intramolecular interactions, this is rotation diffusion. The molecule just performs rotational dynamics. And then those expressions become very simple. This is the simplest relaxation expression. So just this is the form of the spectral density. And tau c is called correlation time. This quantity gives you information how fast the molecule rotates. Of course, it does not need to be water molecule. I just took here water as an example. However, sometimes actually this equation is correct in case the molecule performs isotropic motion. Sometimes in case of complex, not symmetrical molecules, the form of the spectral densities is somewhat more complex. Here you have example. For beta equal 1, you get just this expression. However, this is the simplest relaxation formula, which has a prefactor depending on distance between the interacting nuclei. And here, just quantities, including so-called correlation time, which describes the time scale of the rotation dynamics. Then you have the second contribution, intermolecular. And the second contribution, intermolecular, is much more tricky because it fluctuates in time because of translation dynamics. And well, here again you have a kind of prefactor, but here you have the spectral densities, and the form of the spectral densities is much more complex. I again do not want to explain the details. We will be not solving diffusion equations. I just only would like to give you the idea. So there's a prefactor and expression which now includes not correlation time describing rotation, but translation diffusion coefficient. However, there's more to that. Namely, also this expression includes a parameter which is called d. And d is referred to as so-called distance of closest approach. This is how close two molecules can approach each other. Sometimes this is really tricky for the data analysis. However, well, usually one can, in a relatively good approximation, assume that the distance, the so-called distance of closest approach, is just the diameter of the molecule. However, this is just the message that, in analogy to rotational dynamics, the intermolecular part includes information about translation dynamics. There's a tricky factor here, which we called NH. It's the number of protons per unit volume of the sample. It means it's the number, twice the number of water molecules, for instance, in case we perform experiment for water. Well, you do not always perform experiments for water. However, this number can be very easily calculated. When I always am asked actually what is the expression for it, I apply a kind of common sense. So look, for instance, if you would be dealing with water, one molar mass of water is 18 grams, yeah? And this is obvious. And the density is like gram per cubic centimeter, approximately, yeah? So you can easily figure out that in 1 cubic centimeter, you have 1/18 times the Avogadro number of water molecules, yeah? So you can very easily calculate how many hydrogen atoms you have per cubic centimeter, yeah? And you can make it per cubic meter or whatever. So this is quantity which one can really easily get, and one should not be scared of that. And there are already pieces of software where all that is implemented. So everything what you need is merely understanding of the meaning of the parameters. That this is translation diffusion, this is rotation, correlation time, and what they come from, that they are just intermolecular and intramolecular interactions and so on. Okay, let us continue because I already used half of the time. And here you have, for instance, some relaxation dispersion profiles collected for glycerol. This is what NMR relaxometry is about. Namely, you change your magnetic field. So the experiment works like that. You polarize your sample in a relatively large, high magnetic field. This I mean by polarization, yeah? So you apply magnetic field and you reach this magnetization. Then you reduce your magnetic field to a much lower value and you observe how the magnetization decays. Because at lower magnetic field, the magnetization will be lower, yeah? Again, the Boltzmann distribution. And from this decay, you determine the relaxation rate at this magnetic field. Then you polarize the sample again reduce the field to a lower value, but a different one. Again, measure how the magnetization evolves in time, determine the relaxation time, and so on, and so on, and so on. Eventually, you cover a range of magnetic fields, and we can do it more or less from the Earth magnetic field, which means practically 0, to 3 Tesla at this moment. Actually, 1 Tesla means 42 megahertz for protons. And one gets this type of data. And then, applying such mathematics, one can reproduce the data in terms of that models, and one can determine the value characterizing the motion, the translation diffusion coefficient, the rotational correlation time, so one can learn how fast the molecules move. And you see here very nicely that the relaxation data are decomposed into parts associated with translation and with rotation. Does not matter how it was done, but this is possible, how to say. I mean, it was done using this software. Here you have more ideas, more relaxation data. You can see how they change in temperature, with temperature. What more? If you do not want to analyze data in such a way, so you do not want to, I mean, I always think that actually one should analyze data in such a way. And actually for the purpose of our project, I can give you the whole software. If you, at a certain moment, we will be working on that. I will make it publicly available. It's a kind of user-friendly software written in MATLAB, but you do not see that. You just only tick boxes, yeah, choosing some parameters. So we could try to analyze some data. Okay. But in case you do not want to analyze the data in such a way, I mean, I would like to convince you that NMR relaxometry is not only for looking how things look like, but also one could get really quantitative information. Okay, one can do something else. One can plot the relaxation rate using linear scale versus square root of frequency. And then you should get linear dependencies at the low frequency range, like here. This is, you see, possible because the part associated with rotation dynamics is flat here. So just the slope stems from the part which is associated with translation dynamics. peaks. And then some time ago, well, it is almost 9 years actually, but I think people are still interested in this paper because it's convenient. We derived a kind of expression which allows one to determine translation diffusion coefficient from this low frequency slope. And here you have a kind of closest form expression, which you might say that it looks horrible, but it's not the case. Imagine you have your relaxation data. So you measure them. You have here logarithmic scale and here logarithmic scale. Then you change this scale to linear, and here you calculate square root of frequency and make the scale also linear. Not a very big deal, yeah? Then you just look at your figure and you see that there are linear dependencies here. So you make linear regression. Each software has linear regression. And you get the value of the slope. If you pay attention to units, so for instance, you are not mistaken and you deal here with the frequency in hertz, not megahertz, then you even do not need to bother about what are the units of the slope. Then you apply this expression to the slope and you get the diffusion coefficient. You can say, oh my God, how am I supposed to apply this expression? The point is that, look, to calculate this thing is really not a very big deal. Then here you have well-known physical constants, like vacuum permeability, Planck constant, and so on. They are just well-known quantities. The point, and this geomagnetic factor of protons. This quantity one can just calculate once. Frankly speaking, I can just give you this expression. The value of this part of the expression is just a number. And it never changes, it's sample independent. You calculate it only once. And then you have to calculate only the number of hydrogen atoms per unit volume and multiply it by twice. And from that, you can very easily get the diffusion coefficient. And we did this for very many liquids, and this very nicely agrees with diffusion coefficients measured by any other method, especially gradient NMR. So this is a kind of really straightforward trick, and we could practice it if you like. And you see, for instance, you can hardly measure slow diffusion using gradient NMR because you need some changes in the frequency and the gradient must be very large and there are limitations and some instrumentation is expensive. Just here you can measure really slow diffusion. So I think people like it. But there's even more to that. Look at this figure. I told you that we have the spectral densities here. And I said that, well, for rotational dynamics, you can have such form. If the rotational dynamics is not really isotropic, the form will be more complex. For translation dynamics, it's even more complex and so on. Yep. I just here put, sorry, something happened here. I just plotted the form of the spectral densities because look like that. If you look here, forget the prefactor. Whether you have just the resonance frequency or twice the resonance frequency, this is really not a much difference. So somehow you can say that the relaxation rate is proportional to the spectral density. So if you look at the shape of the relaxation rate, how it changes with the resonance frequency, it's like this reflects, the relaxation data reflect the shape of the spectral density. And here I plotted some forms of spectral densities. So isotropic rotation, translation. Yeah, so you see already here that the shape of the curves is much different. However, there is, as I said, more to that. Here I advise you to plot the relaxation rate versus square root of frequency, and I said that you will get linear dependencies. The point is that not always, because here, especially for instance, if you have food products, which are different kinds of porous matrices and so on, and water is trapped in this matrix, then the water have more or less freedom to move, yeah? So it is not obvious that the water molecules can freely move in all three directions, X, Y, Z. So it's not obvious that the translation diffusion is really isotropic, and I mean three-dimensional in this sense. It may happen actually that, well, one of the direction is blocked by the macromolecular network, the shape of the pores, the confining walls, yeah, and then water in the vicinity of the walls just move close to the surface. So it may happen that actually the diffusion is restricted in one direction. So in fact, it's more like two-dimensional. You see, there's also a recipe for that. So I would put it like that. If you perform such figure, you produce such figure, you use this representation, and you get linear dependencies here, you can be sure that your dynamics is three-dimensional. So you not only get diffusion coefficient, but you have also proven that your dynamics is isotropic. However, it may happen that, for instance, if you use here linear scale and here logarithmic scale, just frequency, not square root of frequency, it may happen that then you will get a linear dependence. And if in such a representation you get a linear dependence, you can also get the diffusion coefficient from it, but you will also prove that the dynamics is restricted, is anisotropic. So this is quite unique potential of NMR relaxometry to reveal how to say the diffusion paths, not only the time scale. Okay, as I do not have much time, I have 3 more slides. Let me check. Okay, I have 15 minutes, but I will be done in 10 minutes. Okay, I have 3 more slides. So let me show you something else. The relaxation data for proteins. A dry protein, elastin and lysozyme, and somewhat hydrated protein. Well, the situation somehow is getting close to the cases of biological systems. Actually, I am stupid. I should have taken, for instance, albumin from egg. However, the data look very, very similar, really. You will get very similar picture. What is happening here? You have the dependence of the relaxation rate on the frequency, but you see here a kind of funny effects, yeah? You see, in fact, 3 peaks, because there are 2 of them, but they are not well resolved. Here they are somewhat better resolved. I could enlarge this a little bit. And here you have another one. And this effect is often called quadruple relaxation enhancement, and those maxima are called quadruple peaks. You will for sure meet the, you will for sure have the possibility to read about that. This will, because this is quite typical effect observed in NMR relaxometry. Actually, for a long time, people thought that this is a kind of artifact. What it is? This is associated with the presence of nitrogen in the sample. Because nitrogen-14 possesses quadruple moment. I mean, yes. And I'm not going to talk much about quadruple interactions because I would need to go deeply into physics. However, let me put it in this way. Those maxima appear at some frequencies. The difference between those two frequencies gives the position of the third one. It's a kind of rule. From the positions, you can determine such quantity, like for instance, electric field gradient tensor at the position of the nitrogen. And the position, in other words, maybe the positions of those effects are very sensitive to even subtle changes in the molecular arrangement. Therefore, it has been demonstrated recently that they are really extremely important for medical diagnosis. However, they can also tell us a lot about changes in food structure. The position, shape, wave. So I just wanted to show you that. So this is the first slide. This is the second one. When you can see that we analyzed the data, for instance, for proteins, yeah, in great detail, and it requires some effort. For instance, you see what the quadruple peaks come from. Yeah, this is one line and this splitting here. And this kind of quantitative analysis, which is maybe not so straightforward, but really tells you a lot about the system. Because as you can perform the relaxation experiment in a broad range of frequencies, you can learn about motional processes of different time scale. Here at lower magnetic fields, you see slow dynamics. Then you see a kind of intermediate dynamics. Then at higher magnetic fields, you see fast dynamics. So this is the point that actually if you perform classical experiments, NMR experiments using high magnetic fields, you can look like at relaxation features of, how to say, individual protons. If you, for instance, have glycerol molecule and there are non-equivalent protons here, because some of them belong to the OH group, some of not, and then you can measure the relaxation rates for them separately. However, you will be only in this range where the relaxation rates stem from fast dynamics. To probe slower dynamical processes, one has to go to lower magnetic fields. And we have the whole range. So we can go from slow dynamics to fast dynamics. And eventually, as I suppose you might have some questions, let me say 2-3 sentences about the last slide. I told you here, we took those proteins, yeah? Just as a kind of model system, and you analyzed the dynamical processes, slow, intermediate, and fast one. Look, we made the same thing for cheese. But actually it turned out here that we do not have slow, intermediate, and fast process. We did here something else. The analysis here is very similar to the analysis which we have done for glycerol, just as a model system. Contribution from translation and contribution from rotation. And here this is our joint paper with Metsit. We have contribution from translation and contribution from rotation. And we just applied this analysis to cheese, and we learned about how water moves in different kinds of cheese. Looking just, you see, not like you measure, for instance, viscosity or something like that. Looking really at the molecules. I mean, this is information from the molecular point of view. And actually following this line, we had quite funny statements that, well, we checked this dependence, this linear dependence, and we stated like, I don't know whether this is of much interest, but you see, we can demonstrate that in cheese, water has the freedom to move in all possible directions. And well, we are able to publish it in quite good journal. So it seems that it might make some sense. So, okay, I do not have any major conclusions. I just hope to entertain you a little bit. So I'm done. Thank you.
Thank you very much, Danuta. I have a quick question. So in cheese, it is clear from the model that you have shown us the translational and the rotational contributions. In the second slide that you showed us this equation. What about the fast, intermediate, and slow regimes? So how that model is going to be modified? Because there we had the two components, rotation, translation. So
here is a different story, because here you see, we intended to study dry proteins, as dry as possible. However, reviewers complained that we have always some water. I said, okay, maybe we have 0.2% of water, but this is not what we are looking at. Okay, however, they really kept saying like that. So I wanted to tell them that even if we would have much more water, because they wanted us to estimate the exact amount of water, and we are not able to do that because I don't know, maybe it was 0.2%, maybe 0.6%. I mean, we tried it as much as we could. So I got mad and I said, okay, let's put 10% of water into the sample and we'll see how much different result we'll get. And then we'll fight with the reviewer. And actually it turned out that for 10%, we got almost the same data. Here for almost 40%, well, the data start to be different. This is actually important here, and the peaks are smaller. However, for 10%, it was almost like nothing. However, here we have dry proteins. So here we somehow demonstrated that even if we have small amount of water, it really does not affect the data. So we'll keep the proteins like dry. And in dry protein, there is nothing to diffuse. However, the proteins themselves perform a kind of complex motion. But really, proteins can move in a kind of crazy way. Nobody really knows how proteins move. So we just decomposed the relaxation profiles into 3 contributions of this kind. And it was a long discussion what they mean, and we put some hypotheses there and so on. However, anyway, we said that actually the proteins are, how to say, engaged in 3 dynamical processes, which can be more or less characterized by such time constants. And we didn't want really much to speculate what it is. Well, however, answering specifically to your question, it was just 3 terms like that.